Great. So next up, we'll hear about real customer stories and where machine learning solutions were developed to support specific business scenarios. So please welcome onto the stage Rina Ahmed, Systems Analyst from IAEA. Please give a big round of applause.
Hi, everyone. My name is Rina Ahmed, and today I would like to talk to you about different scenarios where we implemented with different techniques, AI and machine learning into solutions. So we will be talking about real-life customer stories, and I brought to you case studies from the area of classical machine learning, from deep learning, specifically custom vision, and how we used pre-built AI capabilities with a customer. Just a little bit about myself. I studied at Vienna University of Technology. Then I worked 2 years at UNIDO as a developer. For the past 5 years, I have been at Microsoft. The first 4 years, I was in Microsoft Austria as a technical evangelist. And the last year, I was part of Microsoft Corporation as a software engineer, part of the engineering team. And very recently, barely 3 months, I joined the IAE as a systems analyst. Just to make things clear, in case if you're here today to hear something about my current employer, that is not what I'm talking about. I will only be talking about my work during my previous role as a software engineer at Microsoft. OK, so before I talk about the customer cases, I need to give you a little bit context of who my team was and what we did. So we were commercial software engineering, part of Microsoft engineering. We were like the product groups at Microsoft, except that we did not work and build the products of Microsoft itself. Instead, we were coding together with our customers on their solutions and their products to build into new features or solve hard problems. Also, we would not work on very established technologies or where Microsoft already has out-of-box products. We worked on problems that still needed coding effort to be solved and where we could generate some kind of learning that we could share either with a community or internally or with the customer in form of knowledge transfer. So the sharing usually happens in forms of talks like this, or in forms of open source code on GitHub, and so on. And most of our customers and partners are usually global companies, mostly Fortune 500 companies, but not only. We also work with NGOs, academics, UN organizations, Red Cross, and so on. So if we define that we are going to engage with a customer, then what would usually happen is we define the problem that we were going to work with, and we would code together, Microsoft software engineers together with the software engineers of the customer or partner, on usually a week of a hackfest together, 3 to 5 days, which was preceded by a prep time, especially in AI and ML cases. We would usually get the data in advance so we can do some prep time, or so we can look at the data and determine, is that data good enough that we can actually build something, use it for a model. And then sometimes we would also have follow-up activities. And the technologies that we usually work with are newer. So it can be AI, ML, IoT, blockchain, mixed reality, and so on. OK, so let's start with our customer cases. The first customer case is from a customer who is called HR Focus. They're in South Africa, based in Johannesburg. They are an ISV who create an HR solution. Their customers are in Africa and in Europe, and their customers are in diverse kind of industries. from industries like pharmacy, retail, finance, mining, and so on. What they wanted to do is they wanted to add a new feature to their product for their customers called employee retention. So they wanted to enable their customers to know in advance when employees are going to leave the company. Because the HR process is time-consuming, resource-intensive, you have to write out the roles, do a lot of interviews, and we have the onboarding time until a new employee can become productive. So they want to avoid losing good people. So that was what was the goal of the Hackfest. But because I told you that this customer has this ISV has customers in different industries. Now you can imagine HR data from a pharmaceutical company looks very different from HR data from a mining company. In a pharmaceutical company, you have probably higher skilled people, you probably have more promotions, maybe higher work satisfaction, and so on. Whereas in a mining company, you have workers working maybe in harder physical conditions, maybe having more sick leaves. So a model you develop for a pharmaceutical company is not going to, cannot be equally applied to a company in mining. So for us, it was very important that in that 1 week we were working together with a customer, that we would teach the customer the data science process. We worked with one industry so that they can do it on their own afterwards for all their industries. Our approach was that we wanted to show the customer 2 different ways on how to do things. So we did it once with Python and open source library scikit-learn. And on the other hand, we used Azure Machine Learning Studio. So they can, on the one hand, compare the results, and on the other hand, have 2 different options and can choose whichever they prefer to work with. And finally, we spoke with them about how they can host and deploy the model. So on the right side here, you can see some of the features, the kind of data that we were working with. We had things like age of the employee, length of service, annual leave, sick leave data, how many promotions did they get, what size is the department they work in, and so on. So first of all, we needed to find the relevant data, the features that we wanted to select to train a model. And we started with, this is an example of what we did in our analysis. We did a correlation analysis, so we can see how the different features correlate with each other. And what we wanted to see is we wanted to eliminate features that really strongly correlate with each other, because that might be redundant information. So for example, if you would look at it, you would see things like annual leave or sick leaves taken in the last 6 months correspond or correlate very strongly with annual leave or sick leaves taken in the last 12 months. And that makes sense. If I took a lot of annual leave in the last 6 months, then if I look at a broader time frame in the last 12 months, I've also taken a lot of annual leaves. So these kinds of cases, we had to decide, OK, we're just going to take one of these features. We had other cases like employee ID correlating with a lot of features. But here we knew, OK, employee ID is random. So whatever correlation we find here is purely random. So we defined a couple of features that we thought, OK, these are the features that we want to use in our model. And then we started to look more closely at the different, at the data of the features that we selected. And here, for example, here is an example of age of the employee. And what you can note here are 2 things. First of all, we have quite a lot of people who are the age of 18. And then here we have several outliers of people working past what we thought was the retirement age. So we did not understand this. I mean, of course, maybe this pharmaceutical company has a lot of interns. It could be true. Or maybe something is wrong with the data. Could also equally be true. So you don't know this kind of thing, and you cannot make a decision unless you speak with the domain experts. So in this case, we found out that the ISV who provided us the data didn't just come. They did their own data manipulation, and they actually filled all the missing values of employees who didn't have age with 18, which does not reflect the reality of the work population. So we fixed it by taking the mean age. For the outliers, the problem was that the age was calculated by counting the time between date of birth and today. So all the people who already left the company, they continued to age. So if someone left 10 years ago, he would be 10 years older, and that explains why we have people like one person, 118 years old, working for the company. And yeah, you fix that. Once you leave the company, your age should not be continued to be calculated. We are only interested in the age that you had when you left the company. Another example is where we had features like these, where we have the department size where each employee works, and you can see there's a range of continuous numbers ranging from 0 to 30, and to make it more manageable and to find more meaning, we wanted to group them into smaller sized chunks. So what we did is here, with regard to the active population, we defined our bins, our groupings, and grouped the department size and people working in less than 10-person department, 10 to 14, and so on. And we wanted to create groupings that are quite homogeneous. So you do these kinds of things, and then you have a data set. You clean the data, you look at missing values, and then you have a data that you can work with. And then in our initial run, that was actually prior to the Hackfest, we already had the data to try out, so we did spot checking. We tried out different classification algorithms, because we had one label column active or not, and we wanted to predict will an employee be leaving or not. So this was a binary classification problem. But during the Hackfest, as you saw, we analyzed different things, and we worked with the ISV. We needed a new data set, so we got a new data set. We had to decide, OK, how much of the new data set, how much of the data manipulation are we going to do in SQL, because their data came from an Azure SQL database, and how much are we going to do in Python? So whatever they were really fluent in SQL and felt very comfortable, this was their world. So whatever they felt they can easily do in SQL, they did in SQL, and the rest of the data manipulation we did in Python. And once we had the data set, we uploaded it into Azure Machine Learning Studio. And then we created a model in Azure Machine Learning Studio. What you see here is the workspace, and it works by dragging and dropping modules and connecting inputs and outputs, and this way you can create your whole data science process graphically in Azure Machine Learning Studio. So just what I want to give you a feeling for this. We start with a data set, and then we can do different kinds of data manipulation. In this case, we defined what is the labeled column and which columns are categorical features and so on. And we decided, OK, we tried two different things, and this is a data set that we actually like and we want to continue with. And then we tried 1, 2, 3, 4 different machine learning algorithms. Because this is Azure Machine Learning, these are algorithms developed, machine learning algorithms developed by Microsoft to compare them against each other. And in our case, this binary boosted decision forest algorithm was the one that gave us the best result. So what did we do? We took that algorithm, we looked at the parameters, and then we searched, OK, in scikit-learn, which algorithm has a similar implementation, or would be equivalent to this Microsoft 2 class decision forest. So we decided to go for ADA-boosted decision forest in scikit-learn. And we recreated the same kind of parameters just to compare both with each other. So here we have on the left scikit-learn and on the right Azure Machine Learning. And what we wanted to look at was the recall value, because for the ISV, it was really important to catch all the people who are leaving to be predicted as leaving. We did not, the cost of having false negative was too high for the ISV. They did not want management or HR to be surprised by a resignation of an employee that they did not see that they did not see coming. They could live if employees were actually not intending to leave, but have been predicted as leaving, which would be a false positive, because what would happen in the worst case is that management or HR starts a discussion with the employee about work satisfaction, and it's not the worst thing to happen. So in our case, recall is the value that optimizes, so you minimize the false negatives. Therefore, we looked at the recall value, and as you can see, Azure Machine Learning had a slightly higher value. I have to say that basically, even though it has a higher value, if you want to further optimize this and really go deep into the model and tweak all the parameters, we would probably recommend scikit-learn, simply because it allows you to tweak any kind of parameter there is out there, and you can get the last bit out of performance. And Azure Machine Learning is very good at giving you very quick trying out different models, comparing them side by side with each other. What we also did is we did tuning of hyperparameter. In Azure Machine Learning, it's called tuning of hyperparameter. And in scikit-learn, we used grid search. What it does is we give them a range of value of parameters to test and tell us, OK, which is the best recall value you get for this combination of parameter. And in this case, because we had a limited number of days, we only tested the parameters of the decision tree, which itself is an input of the forest, which also has additional parameters. So we did not do this nested parameter testing of all the combinations, but we started with the decision tree. Yeah, so finally, we wanted to host the model, and what you can do once you have your trained model, which we have here. We just wrapped it around a web API, and we used a Python library called Flask that allows you to do it. And then you write a Docker file. This one takes a Docker image, Python version 3 as base image, and then installs additionally all the library and dependency that our script needs, exposes port 8080 of the container, and then runs the Python script. And then, of course, you have additional files that specify all the libraries that you need. Once you have containerized your model, you can now run it on-prem or wherever a Docker engine runs, or in the cloud on Azure Kubernetes service, wherever you want. Yeah, so this was a tweet of the customer that, they were happy about it afterwards. Oh, and at the beginning, they were really scared of Python, and at the end, they loved Python. That was cool. OK, the next case is about deep learning. And here I want to talk about small-scale mining in Ghana. So Ghana is the second largest gold producer in Africa. A third of the gold comes from small-scale mines, and a lot of it is illegal activity. And it brings problems like health risks, prostitution, child labor, deforestation, water pollution, and so on. And it was a research project of Royal Holloway University in London, who wanted to assess the impact of these small-scale minings. And the problem to assess the impact is, because a lot of it is illegal activity, there is no website or registry that lists, here are all the small-scale mining in Ghana. So we needed to find them. So our approach was first collect all kinds of data on Ghana, get satellite imagery of Ghana, develop a deep learning algorithm that detects all the small scale mines on Ghana satellite imagery, and then do some correlation analysis. So if we look at a map, depending on how much you zoom into it, so if we have a satellite map tile that in 4 tiles, you can see all of Ghana. Then you can imagine if I want to find all the small-scale mines, there are going to be dots in each of the map tiles, which makes it an object detection problem. But if you zoom in close enough so that one tile is actually 1 or 2 mines, then it becomes an image classification problem. So we made it an image classification problem. We built a classifier using Keras and TensorFlow with a pre-trained model, and visualized it on Power BI. And we used the standard data science process. So we used Keras. If you listen to the talk today, it was very simple to use. That's why we used it. We split our data, our satellite images, into training, validation, and test sets. Then we did things like tuning our parameters and got a confusion matrix. And down here you see a GitHub repository where we have the generalized classifier. So if you want to use the same thing to classify, feel free to do so. What Keras does, it gives you different types of pre-trained model. So you don't need millions of images to train your model from scratch, but you can just use train the last layer of the model with your own domain-specific images and build a classifier on top of it. In this case, we used Inception v3. So the problems that we had is, in the initial run, the classifier learned to detect all brown areas of Ghana as a small-scale mine, but Ghana also had brown areas that were not mines. So what you can do is you can fix it with data augmentation, flattening colors, or something like that. But what we did is we labeled more data, and this was extensive work. We were 8 people labeling 6,000 images for 4 hours. That's 36 hours of work, very boring work, but it was essential. Oh, and by the way, our data set was 4 million satellite map tiles to start with, which we were provided by the Bing team. Since we were Microsoft, we could ask them, please give us Zoom level 18 map tiles of Ghana. And we only concentrated on the southern part of Ghana because frankly, we did not have the time to label more image of all of Ghana. And the research student told us that based on different assumptions, more likely small-scale mines are in the south of Ghana. And then we needed to define a third category because we had a lot of clouds that messed up with the classifier. So our 3 categories were is mine, is not mine, and cloud. Yes, and this is the confusion matrix that we had. So we got pretty good results. And the classifier that we built, it's on GitHub. It's general enough that you can use it for other image classification problems. Today, you could probably use FastAI or something, another library like that to help do this quicker. So the last part was to do some data correlation with, we had household data, demographic data, we had health data of the Ghana population, we had deforestation data, we had lighting data. So we had a data set of 135 rows and 700 features. A lot of these features had some random, not random, it had some numerical label that made no sense to a human, and then there were separate Excel files that mapped those numbers to something humanly understandable, like this is income, or this is whatever. So with 700 features, this was really hard for us to grasp what are we even looking at here. So we decided, OK, let's just take a super small subset of the data, about 10 to 15 features, and try to see what can we get out here in terms of correlation. And all of our data showed things like this one, this image, which is the correlation of accidents or illness incidences according to the distance of the next mine. So as you can see, of course, if we're closer to a mine, we have more data points. The further we get less data points. But you cannot see a clear trend because there's still a lot of illnesses and accidents also the further you get. But here you can see some kind of trend. This was the only place where we found a correlation. This was the further away you get from a mine, the less deforestation happens. Oh yes, and then there's this tool that we tried to use, IDR. It helps you to do those data exploration stuff. It didn't work in our case because we had 700 features, and this tool also could not handle it. But it's a nice idea if you have a more manageable data set. OK, the last, no, not the last case, but this case is from a customer that I cannot tell you the name, and I cannot also explicitly tell you what kind of products they have, but they're in retail. They have products. They have images of their products, and we needed to classify their products. The customer already came with 33,000 images for training and 10,000 images for tests for their products already labeled in the different categories because the customer actually had done his own research and already evaluated TensorFlow and some other deep learning model. And he came to us because he specifically wanted to say, OK, how do the Microsoft services compare to what he has already used? So it was kind of benchmarking. So what we did is we wanted to compare, first of all, custom vision, which is pre-built AI, already trained model, hosted, and you can just send your data and get your results in a REST API, versus Azure Machine Learning Custom Vision package, which was something that Microsoft released for task-specific machine learning scenarios that already had the steps in a Jupyter notebook outlined. So you did not have to write all of it yourself. And we had scenarios for custom vision, for text analytics, for financial forecasting. I must say this tool today, as of September, it is deprecated, so this tool, yeah, you can't use it anymore. But we compared these two things with the customer. Also, the customer wanted to know the top 4 accuracy. So he didn't want to know what the accuracy is, whether the image is correctly predicted, but whether the image is correctly predicted in the top 4 predictions that we get. That was good enough. And this was what he tested with TensorFlow. So we needed the same kind of evaluation so he can compare. He had something 92% accuracy for TensorFlow, and I don't know about the other. And then we discussed about running AI because he had a very custom retail device that I cannot specify near this. It was not a PC, but it ran Windows 10. And it was small. It did not have a lot of memory. And he wanted to run in an offline scenario this trained model. So this model had to be small in size, and the inference had to be very quick. The milliseconds mattered. So we used, I'm not going to talk about custom vision, because I think we've heard, probably you've heard in some of the other talks about it. I'm going to talk about CVTK, which again is deprecated. This is the standard code. So this is, in this case, what it does, it uses CNTK. And it provides a higher layer of abstraction to use CNTK. So we had our test set, and we can split it into train test, which we did not do because the customer already came with his own data split, which we respected. And then you can do image augmentation. We found out that in this case, for his product, image augmentation actually made the results worse. So we didn't use image augmentation. And then you can train your model and get the results. But what this gets is the top 1 accuracy. So we wrote our own custom evaluation for the top 4. Basically, what we did is for each image ID, we took the top 4 predictions and stored a list of human-readable product names of the top 4 predictions. And then we also, for each image, had an array with the true label of each image, and we compared if the true label is in that list of top 4 predictions, and if yes, we stored it into a true-false vector, and then we just calculated how much true cases do we have. And that was our top 4 predictions. So as you can see, top 1 prediction was 92%, top 4 was 95.5%, and this was the customer threshold, which we had already reached. And this was just using the default parameter of CNTK, which you could, of course, now further tune, but for the customer, this was good enough. And then he wanted to run this on this custom device, so we talked to him about WinML. He could WinML, which allows you to import models, and you can build a Windows app and run it on the device. But he also had an Intel Movideo stick, which also allows, which you can attach to it and then run very fast inference on it. But that one only supported TensorFlow. So I'm not going to go in detail about it. I think there is a whole session, Building the Intelligent Edge, where you can find more information on that. So the last case is using pre-built AI technologies, and Microsoft has different services in the area of vision, speech, language, knowledge, search, and labs. And this case that we had was around custom machine learning, custom machine translation. Again, here I cannot tell you the name of the customer, but he had would write a lot of documentation for his customized product. So if all the documentation he writes for one customer would be printed, it would be large cardboard boxes like this for filling half of a room. So they do a lot of documentation. It's a multinational company, so it needs to be translated. They have their own team of writers and translators, all human translators. And they are in an industry that is so heavily regulated, where if you make a mistake, it could result in human death. So it was machine translation could never replace human translation, but they wanted to make the process more cost efficient by using it as a first-tier translation, so that human translators only go over it, what is already translated, and fix it. So they had a lot of parallel documents. We used one language pair. We had a training, tuning, testing set. We uploaded all the data and deployed it. You can all do this via Microsoft Translator Hub, and then built it, consume it via REST in a client. The first results were actually not very good. They told us that DeepLink, which is one leading provider in machine translation, had better out-of-the-box translation. Also, Google Translate had better quality translation than the customized Microsoft translation. However, this text-to-text translation was based on statistical machine learning. And during our engagement, Build conference happened, and Microsoft announced that now we have text-to-text translation based on neural networks, which was much better and gave better results. Yes, this is how the interface looks like. Yes, so in summary, I showed you different cases with different kinds of technologies and different levels of AI machine learning that we used. What we talked about is we used Keras and scikit-learn and TensorFlow and CNTK. Azure ML Workbench with the custom vision package, which is deprecated now, Azure ML Studio. I didn't speak about it, but we used the data science virtual machine with GPU, which I needed for the deep learning. And then we used Azure blob storage, where our data was stored, Azure machine learning and cognitive services. But what I wanted to show you is some things were run on premises, some things were run on cloud. We used open source technologies together also with Microsoft technologies. We looked at what does the customer need in this scenario, what is the best technologies. We also tried not to force the customer to use a technology that he does not want to use, or to use a technology that is maybe awkward in this scenario, and maybe it's better to just learn a new technology if it just does the job in a faster or easier way. Yes, thank you for your attention.
Thank you. So thank you very much, Rina, for the really informative talk. I think we have time for one question, unfortunately. If your question is not answered, then please find Rina near the stage later on. Please, Rina, so out of these questions, which one would you like to answer? You get to pick one.
OK, so I cannot tell you about the GDPR compliancy because, I don't know, this was a company based in South Africa, and yeah, I don't know. We did not ask about that here. Also, we were far from having it into production because, as I told you, they would need to continue to work on their own to actually build the models for all the different industry before it could go to production. So our goal was just to teach them how to do the data science process. Mm-hmm. And plus, we're just software engineers. We cannot talk about legal regulations. We're not even allowed to do that. How long was the Ghana project and person days needed to deliver an ML model? So the Ghana project was a week. We were 8 people on site, but we were also some people working on it before remotely, because the labeling of the satellite images was just a very long, time-consuming task that needed to be prepared before as well.
OK, I can imagine. I think we're seriously running out of time, so we'll have to wrap up here, unfortunately. Please find Rina in front of the stage or near the stage, and please give her a really big round of applause, and we will meet again at 5:30.